This will be a short video where I will solve a few of the chapter problems from chapter 9 related to Six Sigma. Um, this is problem 9.1 at the end of the chapter. It says Multi-Sigma Corporation has a process which they believe is operating near the Six Sigma level and want to verify this. If the specification for a critical part in the process is 2.8 centimeters plus or minus 0.1 and the standard deviation for the process is 0.169, at what sigma level is this process operating? So in this case we have the tolerance range is 2.9 to or yeah, I should say it's 2.7 to 2.9. So using equation 9.1 in the book, we know that K times sigma is equal to tolerance range divided by 2. So in this case, solving for K, and we know 0.0169 is the standard deviation, and our tolerance is 0.2 divided by 2. K will be 5.92. Now we can use that information to compute DPMO for this problem, and to compute the DPMO we say equals DPMO is parts per million, so defective parts per million, so 1 million times and 1 minus norm distribution. We essentially want to find the probability of a normal distribution at the point where x is 5.92. So I'm going to treat 5.92 or the sigma level as the x value here. So I put 5.92. The mean, remember, given the discussion in the chapter and what I showed in the other video, the mean could be allowed, the mean of the process or center of the process is allowed to deviate or shift for 1.5 sigma levels. So the mean will be could shift either in either direction away from the center, which the center is 0. So then the mean could be 1.5. Standard deviation is 1, and we want cumulative, or I can put true, and we get 4.93. So given that sigma level is 5.92, then approximately 4.9 defects per million opportunities can be expected. This was the situation where we did not know the standard deviation. In this problem we do, oh no, in this one we also don't know the standard deviation. Oh no, wait a second, in this one we did know the standard deviation. This is where we don't know the standard deviation. So Never Flounder, this is problem 9.2 at the end of the chapter. Never Flounder Fish Company advertises that 98.7% of their fish were caught within the past 36 hours and that all of their products are 100% fresh. How many DPMOs does this claim represent, and at what sigma level is this process operating? So if they are saying that 98.7% of the fish is fresh, then 1 minus that would be 1 minus 0.987, or 0.013 is the defect or the not fresh. So times a million, the DPMO would be multiply this by a million and you get 13,000. So 13,000 fish would not be fresh per million given this claim that they have made. So that's DPMO. And at what sigma level is this process operating? In this case, there we go. Or I can write it first. In this case, we want to use the norm because we don't have the standard deviation in this case. We want to use the 1.5 shift in our calculation. So we use norm standard inverse of the standard normal distribution. And again, we want this point right here where 9.987 that marks the 0.987 point on the curve. So 0.987, but we want to add the process shift can be 1.5. So we want to add 1.5 to that. So in this case, norm SN 0.987 plus 1.5, and we get 3.7273 almost sigma. And of course, if I were to compute for this sigma level, if I were to use 1 million times 1 minus norm dist, where we have 3.726 as our x value, 1.5 as our mean, 1 as the standard deviation, and we say true, we get that 13,000 that we had calculated here before. Given rounding, because I used 3.726 in my calculation here, whereas I had rounded. This is problem 3 at the end of the chapter. It says during 1 month, CIC processed 25,000 invoices for Alpha Corporation, 23,000 for Beta, and 8,000 for Gamma. Of those, 205 from Alpha, 175 from Beta, and 103 from Gamma were defective or had errors. They had to be reprocessed. What is the overall defect rate and the sigma level for all of the combined batches, and then for each individual batch? So to get the combined, we have 205 plus 175 plus 103 total divided by all of the opportunities for error, which are 25K, 25,000 plus 23,000 plus 8,000. And that gives us 0.0086. So defects per million, DPMO, would be 8,600. Now, to compute the sigma level for the combined process, we would use the standard inverse of the standard normal function. So norm SINV, and if 0.0086 is our defect rate, then 1 minus that, 1 minus 0.0086 would be our non-defect rate. And but to that I want to add a 1.5 sigma shift, and so the process sigma level for the entire process, for the combined process, would be 3.88. Obviously, if I were to reverse it now and use my normal distribution, I would get 8600 as the DPMO for this process. Now, then the question says, what about each individual batch? So I'll just do one of them. For alpha, for example, for alpha we have defect rate. Do it over here. For alpha, the defect rate was 205 divided by the 25,000. And that would be 0.0082. And then using exactly the same thing as we did with standard normal inverse, we would have norm.s.inv. Our defect rate, 1 minus our defect rate is 0.0082, and then I'll add 1.5 shift. And so it looks like this, or alpha, the processing of the claims or of invoices for the alpha has a higher sigma level than it does for the entire process. For the entire process. Okay, and so now problem 9.5. This is similar in a way, but the opportunities are constant. So let's read this. Nanos electron manufactures 75,000 circuit boards per month. A random sample of 800 boards is inspected every week for 3 characteristics. Quality characteristics are monitored. During a recent week, 4 defects were found for 1 characteristic. So 4 was found. Oops, not there. 4 was found for 1 characteristic. 2 defects was found for another characteristic, and 1 defect was found for the 3rd characteristic. If these inspections produce defect counts that were representative of the population, what is the overall sigma level, and what is the sigma level for the characteristic that showed 4 defects? So again, what we need to be careful of here in this problem is that because 3 different quality characteristics are being monitored, even though we are sampling 800 units only, but the opportunities are 3 times 800, or 2,400 defects, 2,400 opportunities for failure or for defect. So in this case, we have 4 plus 1 is 5 plus 2 is 7. So 7 total defects divided by 2,400 is our defect rate. And then if I multiply, and let's see what that is. That one is 0.002917. 0.002917, which if I multiply that by a million, DPMO is 2,917. So that's our overall defect rate, and overall for the process DPMO. But then it says, what is this? Oh, and then we need to compute the sigma level. So again, the sigma level equals the norm S, norm S inverse of 1 minus the 0.002917 plus a shift of 1.5. So we get 4.26 almost as the sigma level for the entire process. Now, if we do the same thing, but just for the quality characteristic that we found 4 defects for it, then we have 4, but then since it's only one quality characteristic and we had a sample of 800, then it's 4 divided by 800. So, right, 4 divided by 800, and so the defect rate would be 0.005. And so times a million, that'll be 5,000. The DPMO would be 5,000. So with that, then we can compute the sigma level. Again, norm dot S dot inverse of 1 minus 0.005 plus 1.5 gives us 4.076 almost rounded. So this for this quality characteristic we're operating below what the overall is for the for all 3 quality characteristics, and so this would be something where we might be interested to do some analysis, find out what the problem may be, do some root cause fishbone diagram, maybe Pareto charting, something like that. Okay, thank you.